Hello everyone, I'm Yujeong from KAIST. Today I'm going to talk about LazyBatching. This work is done with my colleague Yunseong Kim and Professor Minsoo. First, let me explain what batching is and its effect on latency and throughput. When multiple inputs are to be applied to the same weights within a machine learning model, we can construct a batch and execute the multiple inputs simultaneously. As batching helps share the same weights, it improves locality, which improves the efficiency of DNA computation. In this graph, we show the effect of batching on latency and throughput of ResNet 50. You'd notice that the effective throughput increases as batch size gets larger thanks to increased computation efficiency, amortizing the inference cost and leading to a sharp reduction in average latency per input. Unlike batching for training, however, batching for inference can be challenging on multiple aspects. In training scenario where a DNN framework utilizes a training dataset to generate batches, all training inputs are available before the training begins. On the other hand, for inference scenarios, the task scheduler does not know when the next request will arrive at the server, making it challenging to decide which inputs to batch together. To address such challenges, current DNN inference batching system utilizes the following batch parameters to tune the efficiency of batching and optimize server throughput. First, an inference server is configured with a maximum batch size, which designates the maximum number of input requests the server would wait to batch a request. In this example, the maximum batch size is set up as 3. So, once the batch of maximum batch size is formed, the scheduler starts the execution of the batched input using the DNN model. However, blindly utilizing max batch size alone as a tuning parameter is suboptimal. Consider the scenario where the request traffic is light. As a maximum batch size of 3 forces the scheduler to wait until the 3 requests are formed, the batched request can violate its SLA latency target. To address the aforementioned challenges, current inference batching system also utilizes a tuning knob called batching time window, which designates the maximum window of time the scheduler will wait for a request to form batches. So in the given scenario, because the batching time window elapsed, rather than waiting for the third request, the scheduler just decides to start execution with a batch size of 2, even though the number of requests batched together is less than max batch size. Overall, as you can see through these examples, state-of-the-art batch schedulers utilize both batching time window and max batch size simultaneously to tune and balance latency and throughput for a given DNN model. While a tuned batching system works well for a given model for a given traffic pattern, the statically tuned batching parameters fail to dynamically adapt to varying traffic patterns, resulting in reduced throughput. First, suppose a case where request arrival rate is high. If we set a large time window, we can batch many requests at the same time, and it allows the scheduler to achieve high efficiency. On the other hand, if the number of requests coming in is reduced, and the scheduler still utilizes a large time window, hoping that more requests to batch are coming in, this large time window will unnecessarily delay the request from executing. Consequently, if the traffic is light, having a small time window will be the optimal choice as it provides fast response time. However, utilizing a small time window when the request traffic is high prevent the scheduler from forming a large batch of requests as the time window expires quickly. Thus, statically fixing the batching parameters fails to adapt to dynamically fluctuating traffic and prevents the scheduler from forming an appropriate batch. The second challenge with conventional batching system is the rigid, coarse batching granularity at the entire graph level. Consider a scenario where a new request arrives in the middle of the execution of an ongoing batch. Because current batching system batches in the granularity of model execution graph, the request arriving later is inserted into the waiting queue until the previous batch completes execution. Only when the execution of the previous batch is completed, the waiting request could then proceed with execution. We observe that such coarse-grained graph-level batching loses significant opportunities for batching, as the only condition that needs to be met for batching input is whether the subject's inputs share a common layer weight. Specifically, if we can enforce the previously executing batch temporarily stall and allow the waiting new request to catch up the progress of the previous batch, all three requests can simultaneously execute as a single batched input starting from the third layer. Motivated by such key observation, we propose LazyBatching, an SLA-aware batching system for cloud machine learning inference. The benefits of LazyBatching comes from its flexible and efficient batching algorithm that enables fine-grained node-level batching. Such feature guarantees the inference server to achieve low latency and high throughput in a robust manner across various server traffic patterns and workloads, achieving high SLA satisfaction. So how does LazyBatching work exactly? Let's assume a situation where the first request A arrives to the server and proceeds execution as a single batch input. When another request B comes in, LazyBatching pauses the execution of request A at the end of layer 2. We then context switch the execution to request B and allow request B to start execution until it catches up the progress of the preempted request A. Now suppose request C arrives to the server in the middle of the execution of request B. Similar to the previous scenario, LazyBatching can preempt request B and have request C start execution. Once request C completes the first layer's execution, both request B and C now are ready to execute layer 2 together as a single batch. And after request B and C complete the execution of layer 2 together, we reach a situation where requests A, B, and C can all execute the third layer concurrently as a unified batch. As batching is done in a lazy manner, our proposed batching mechanism allows us to adjust the batch size in accordance to the request traffic. Now, a key concern with such lazily batching mechanism is whether the iterative preemption and context switching can lead to the violation of SLA target due to the elongated latency. We address such issue with our SLA slack estimation algorithm, which is used to intelligently batch requests only when lazily batching upcoming inputs do not violate the SLA target. An SLA slack can be derived by subtracting the summation of estimated latencies of batched requests from the SLA target. Consider the following example where requests A and B are currently being executed as a batched input, and a new request C arrives to the server queue. We first consider the time that request A waited inside the server queue until it starts getting executed. We then add up the estimated execution time of requests A and B. followed by adding the estimated time for the newly inserted request C. In the given example, because batching request C is not estimated to violate SLA, LazyBatching proceeds by lazily batching request C. However, if the estimated latency exceeds the SLA target, our batching algorithm does not seek to batch request C and allow requests A and B to complete its execution, guaranteeing SLA satisfaction. Now, the one remaining piece of the puzzle is how exactly do we estimate a given batch's input latency. For DNNs with a static graph topology, such as convolutional neural networks, the total number of layers executed is fixed at design time. So the end-to-end inference time is the summation of each layer's execution time, which we use profiling to get a precise estimation of. However, dynamic DNN, such as recurrent neural networks used in today's sequence-to-sequence models, have an input-dependent, runtime-determined execution characteristics. Machine translation is an example application of sequence-to-sequence models. When we translate a sentence into other languages, the number that a recurrent layer is repeatedly executed varies depending on which language we are translating into. In this example, for instance, depending on which language we are translating the input sentence into, the length of the output sentence will vary. Nonetheless, a key observation of our study is that the output sentence length for a given sequence-to-sequence pair typically falls within a certain range. The graph shown illustrates the number of words in a sentence in a natural language processing training dataset. As shown, most sentences consist of less than 40 words. As the output sentence of the machine translation inference is affected by how the model has been trained, we empirically observe that the number of words in the generated output sentence at inference time is likely to be less than 40 words. Consequently, when estimating the output sentence length for a sequence-to-sequence model, we estimate that its output sentence length is 40 for a conservative slack estimation. Now let's move on to discussing our evaluation result. To evaluate the effectiveness of LazyBatching, we designed an in-house cycle-level simulator modeling Google TPU-style systolic array. In terms of benchmarks, we chose a wide selection of popular CNNs, RNNs, and attention-based models. For each model, we constructed inference workloads where request arrival rate follows a Poisson distribution. In the remainder of this presentation, we'll elaborate on the effect of LazyBatching on latency, throughput, and the reduction in SLA violations. Due to timing constraints, this talk will primarily focus on ResNet. For more detailed evaluation results, please refer to our paper. First up is LazyBatching's impact on average response time. Here we compare LazyBatching against 4 baselines. Serial is a scheduler that does not apply batching at all. And the remaining 3 configurations are the baseline graph batching with 3 different batching time window values set as a batching parameter. For low traffic, graph batching with time window of 5 provides fast response time as a short time window prevents the server from needlessly waiting for other requests to arrive. However, having such a short time window limits the number of requests that can be batched together, reducing our throughput and aggravating average response time when the load is very high. Graph batching with time windows of 95, on the other hand, helps reduce average response time for highly loaded traffic, as it helps batch a large number of inputs and amortize the latency in preparing for the batch. However, large window graph batching suffers from high latency for low traffic scenario, failing to provide robustness. Unlike the aforementioned two baselines, our proposed LazyBatching successfully adjusts the batching granularity per request traffic, achieving low latency for both low and high traffic scenarios. Thanks to its ability to batch requests when it helps balance latency and throughput. Thanks to its ability to intelligently seek batching, LazyBatching achieves significant throughput improvement than any configuration of baseline graph batching scheduler. Finally, in this chart, we quantify the impact that LazyBatching has on SLA violation rate. In the x-axis, we sweep the value of the SLA target from 20 milliseconds to 100 milliseconds and measure the resulting SLA violation rate, which is shown on the y-axis. For all studied SLA targets, serial and all graph batching configurations suffer from non-negligible SLA violations. On the other hand, our proposed LazyBatching, which intelligently estimates the SLA slack, significantly reduced the number of SLA violations. To conclude this talk, we propose LazyBatching, an SLA-aware batching system optimized for cloud machine learning inference. LazyBatching significantly improves user response time, throughput, and SLA satisfaction by utilizing node-level scheduling and SLA prediction algorithm that can estimate the end-to-end inference latency. On average, our proposed solution achieves 15 times improvement in latency, with a 1.5 enhancement in throughput, all of which is achieved while still achieving high SLA satisfaction.